So the goal of this project is to understand what sets the final mass of gas giants. What sets the mass of Jupiter, Saturn, and extrasolar gas giants. And it's a, okay, where does this work? Okay. It's a bit odd presenting this project here at the Center for Computational Astrophysics, because as you'll see, this project is mostly analytical. But I'm not the first one today, and I'll try to convince you that there is a regime of gas accretion onto planets which is described more easily analytically than numerically, and this is the subthermal regime. So in general, we can define a radius of influence for a planet accreting gas from a circumstellar disk, and this will be the smaller of the Bondi radius and the Hill radius. So the Bondi radius is where the gravity of the planet overcomes the thermal motion of gas molecules, and the Hill radius is where the gravity overcomes the tidal force from the star. And one way to define the thermal mass is the mass for which these two radii are equal. So for any mass below the thermal mass, the planet's edge is defined by the Bondi radius, and this is smaller in this regime than both the Hill radius and then h, the scale height of the disk. And you can define anything within the Bondi radius as being part of the planet, and anything outside the Bondi radius is unbound to the planet, it's part of the external disk. And what these relations imply is that the gas accretion onto subthermal planets is more or less spherically symmetrical. So you can see this geometrically here, since the planet is completely embedded inside the nebula. And also, since the Bondi radius is smaller than the Hill radius, you can show that the shear velocity, the rotation velocity of the infalling gas is much smaller than the free fall velocity. And this means that the gas doesn't have to lose angular momentum to be accreted by the planet. So in the subthermal regime, an accretion disk does not necessarily form, and the accretion is more or less classical spherical symmetrical Bondi accretion. And this is very different from the more complex picture that we have for more massive planets. So now we want to understand or to calculate how planets accrete gas in this rather simple regime. So the first thing to appreciate here is that gas accretion is essentially gas cooling. So the gas inside the Bondi radius radiates away its gravitational energy, cools down, and contracts. And this is essentially the same as the classical Kelvin-Helmholtz contraction that was originally suggested for the sun in the 19th century. And in our case, as the gas inside the Bondi radius cools and contracts, it allows for fresh gas to come in through the Bondi radius to take its place. And this is exactly how the total mass inside the Bondi sphere grows over time. This is how cooling is translated into accretion, into growth of the planet. And when you calculate this cooling time, which is essentially the growth time of the planet, you'll find that it gets shorter as the planet grows in mass. And that's why we say that planets enter a runaway growth phase. So they enter a phase where the mass doubling time gets shorter and shorter with mass, so they keep doubling their mass at an ever faster rate. So the runaway growth is essentially a thermal instability, in a sense. And the question is, what stops this thermal instability? Why would this runaway accretion stop at any specific mass? Why would it stop at a Saturn mass, at a Jupiter mass, or at any other mass? So that's our goal here. So first, there's another limit to the accretion. Gas can only flow at a finite velocity through the Bondi radius at the speed of sound c. So this introduces another limit. This is the classical Bondi rate, which depends on rho, the density of the gas at the Bondi radius. And you can do this exercise. You can substitute for rho the density of the nebula, and you'll find that the accretion rate is still too fast. It's not able to slow down this runaway growth. But of course, as we know, there's another process taking place here on a larger scale. This is the gap opening process. So you can show that because both the planet and the gas orbit on Keplerian orbits around the star, the planet's gravity generates density waves that travel away from the planet, dissipate, and impart orbital angular momentum to the gas. So these density waves act as repulsive torques that push the gas aside and open this gap, this annular density cavity around the planet's orbit. And if you now try to calculate the Bondi accretion rate from within such a depleted gap, then you can show that this is able to stop the runaway growth. So wait a minute, you might be surprised that I'm invoking a gap opening for subthermal planets. That's because if you read the classical gap opening literature, you'll find the claim that only planets above the thermal mass are capable of opening gaps in their disks. And the reasoning here is that these density waves that the planet generates have to dissipate in order to transfer angular momentum to the gas. Otherwise, these waves just travel back and forth to the planet and they don't change the density of the disk. And you can show that only planets above the thermal mass generate nonlinear density waves that immediately shock and dissipate. However, this logic is incomplete because you can consider planets below the thermal mass. So these planets generate only linear density waves, but these linear density waves are essentially sound waves. And as such, their velocity, the speed of sound, depends on their amplitude, on sigma, the density of the gas. So this means that peaks travel slightly faster than valleys. So at some point, the peaks will catch up with the valleys. And like a wave in the ocean, at some point, the wave will steepen, and then it will shock and dissipate at a location that was originally calculated by Goodman and Rafikov. So this means that even linear density waves eventually dissipate and impart their angular momentum to the gas. And in turn, this means that even planets below the thermal mass are perfectly capable of opening gaps in their disks. And in fact, and this was recently shown in multidimensional numerical simulations, even planets as low mass as the Earth can open gaps in their disks under the right circumstances. Okay, so now we want to answer the questions, how can planets continue to accrete gas even after opening a gap? And then why would this accretion stop at any specific mass, at the mass of Jupiter, Saturn, or at any other mass? Okay, so we need to take a deeper look. So here we have an example, a gap opening simulation, a 2D gap opening simulation by Jeffrey Fung et al. So the color map here shows the gas surface density. And you can see that the planet opens this, this gap, this low density cavity around its orbit. But you can also see that although this gap is depleted by orders of magnitude compared to the ambient disk, it is still not completely empty. There's a finite density, a finite gas density inside the gap. And therefore, the planet inside the gap can continue to accrete at a finite Bondi accretion rate. So obviously, the quantity that we need to calculate is this density, the density inside the gap. This is the density that the Bondi radius fills. This is the density that determines the Bondi accretion rate. We can plot it in another way. We can plot the density profile. Sigma is a function of radius. We mark by sigma naught the unperturbed density. And our goal is to calculate the depth of this gap. Our goal is to calculate sigma gap, the density at the bottom of the gap. This is the density that determines the accretion. And in the last several years, there's been both a numerical and analytical progress in the calculation of these gap depths. And the idea is that you write down an expression for the repulsive torque that carves out the gap. This expression depends on sigma gap, the density inside the gap. This is because this is where the density waves are being generated. And in equilibrium, this repulsive torque is balanced by the viscosity of the gas, which we usually parameterize with the Shakura and Tsunaev alpha parameter. So the viscosity tries to smear out this perturbation, and in equilibrium, these two torques are equal, allowing one to solve an equation for sigma gap and to find the density here at the bottom. However, this is in equilibrium. But equilibrium takes some time to reach, and by the time this gap reaches equilibrium, the planet here can continue to accrete gas and grow in mass. So by the time that we think that we've reached equilibrium, we actually are now dealing with a much more massive planet that is now expected to open a both deeper and wider gap, which takes an even longer time to reach equilibrium. So as you can imagine, there's a possibility here that these gaps never reach equilibrium, They just keep on deepening and widening as the planets grow in mass. So obviously what we need here, it's not enough to have an equilibrium theory, which was the focus of most previous studies. We actually need to have a time-dependent theory for the density at the bottom of the gap as a function of time before equilibrium is reached. And just to get a sense of how you write down such a theory, you basically write down an angular momentum conservation equation. So this torque that opens the gap depends on sigma gap, the density at the bottom. And given some time t to carve out the gap, this torque will change the angular momentum of the disk and thereby change the shape of the gap from, say, this black shape to this brown shape. And you can show that this transformation, in order to do it, you have to change the angular momentum by some amount, which depends on sigma naught, the density near the edge of the gap. This is because the center of the gap is already depleted by orders of magnitude, so most of the mass and most of the angular momentum are located here near the edge. So when you write down an equation like this, you can solve it, and you find that the density at the bottom of the gap drops like 1 over t, where t is how much time the planet had to carve out the gap. So this is way too simplistic. What we actually do, we solve for the density profile of the gap, and we follow the propagation of density waves across this gap. And when you do this properly, you can show that you still get a power law, but it's not that simple. It's not 1 over t. It's a slightly different power law, but the motivation or the intuition is given by this slide. Okay, so now let's put everything together. So this is the important slide. This is the money slide. So here we plot the planet's growth over time. So here the x-axis is the planet's mass m, and the y-axis is the planet's mass doubling time, or growth time, m over m dot. So our planet starts over here at low masses, and gradually it moves to the right as it grows in mass. Okay, so initially the planet's growth rate is determined by this Kelvin-Helmholtz timescale, which gets shorter and shorter as the planet grows in mass. However, the planet's growth rate is also limited by the Bondi accretion rate. And since these planets are massive enough to open gaps, we are talking about the Bondi accretion rate from within a gap. And this is given by this blue line, and we can calculate its shape. So the Bondi accretion rate, m dot, depends on sigma gap, the density inside the gap. And as we've seen, this drops as 1 over t. So if you integrate this equation, you'll get that the growth time grows exponentially with the mass of the planet. Again, it's not exactly an exponent because it's not exactly 1 over t. Instead of an exponent, you get just a very steep power law. You can show that the growth time grows as the mass to almost the power of 15. So this is a very steep blue line. Now the overall growth time, which determines the planet's actual growth rate, is given by the longer of these two timescales, the green timescale and the blue timescale, whichever one is the bottleneck. So initially the cooling time is the bottleneck, but when the planet reaches about half a Jupiter mass, the Bondi time becomes the longer timescale, and this ends the runaway accretion. You can see that from this point onwards, the growth time no longer gets shorter and shorter as a function of mass. Quite the opposite, it gets longer and longer as a function of mass. And at some stage, the growth timescale becomes so long that it exceeds the lifetime of the gas disk, in this case chosen to be 3 million years, this horizontal dotted black line. And this intersection is what sets the planet's final mass. So the planet reaches its final mass when it won't be able to complete its next mass doubling before the disk disappears. And you get more or less the right scale for these parameters. Now this blue line assumes that gaps never reach viscous equilibrium. It assumes that the only thing that limits the depth of the gap is how much time the planet had to carve the gap. But for any finite viscosity, for any finite alpha, at some point the gap will reach equilibrium, and then the curves will follow one of these red lines depending on the value of alpha. But what is important here, you can see that if alpha is low enough, in this case lower than 10 to the minus 4, gaps never reach this equilibrium before the disk dissipates. So if alpha is low enough, you can treat the disk as being purely inviscid for the problem of gap opening. For a higher alpha, that's not true, and you become limited by the viscosity, so you can grow to slightly larger masses. Okay, so this plot is for a nominal distance of 10 AU from the star. We can now repeat the same calculation. We can calculate this intersection as a function of separation. So that's what we do here. We plot the final mass of the planet as a function of separation from the star, and this is given by this blue line. So you can see that for 10 AU, we get more or less this one Jupiter mass. At 100 AU, gaps are more difficult to open, so planets can grow slightly larger to 5 or 6 times the mass of Jupiter. And again, this blue line assumes that we never reach viscous equilibrium. If we are at viscous equilibrium, then the final mass is given instead by one of these red lines, depending on the value of alpha. And the way to read this plot is that for, say, alpha equals 10 to the minus 4, at any distance beyond about 5 AU, gaps never have the time to reach equilibrium within the disk's lifetime. If alpha is equal to 10 to the minus 3, then you have to go to about 50 AU for this inviscid limit to be valid. And this inviscid limit, the blue line, gives a rather simple expression for the final mass of a gas giant. So this is the expression. This is the final mass a gas giant is expected to reach theoretically from these gap opening considerations. And you can see that the final mass depends on the disk's lifetime, but only very weakly so. And this is a direct result of the steepness of this blue line. So it doesn't matter how I change the disk's lifetime, the intersection doesn't move too much. So we almost don't depend on the disk's lifetime. We do depend on h over a, the aspect ratio of the disk, its height over its radius. And we depend on rho naught, the ambient unperturbed density of the disk, which is basically a parameterization of the total mass of the gas in the disk. And most importantly, this final mass does not depend on alpha. It does not depend on the Shakur and Tsunaev viscosity, or on any viscosity, because we are in the inviscid limit. And this is very different from some previous studies that tried to calculate the same thing. So at least some previous studies assumed that we are in viscous equilibrium, always, even when it wasn't reached. And then they give the result as a function of alpha. But since this alpha is so poorly constrained, we don't really know what's the viscosity, it's not uncommon to see a paper that varies alpha from 10 to the minus 6 to 10 to the minus 2. And then the alpha-dependent result is not very useful. In our case, the result does not depend on alpha at all, as long as alpha is low enough, or as long as that we are far enough away from the star, in a way that we try to quantify in this plot. Okay, so it would be nice to compare this theory to observations. But the theory has several simplifications that are valid only at large distances from the star. Most importantly, the assumption that planets never cross this thermal mass. And one technique that is effective at such large distances is directly imaging the planets themselves. And probably the best system to compare to now is the HR 8799 system, which has 4 directly imaged planets orbiting the same star. And these planets span distances from between about 15 AU for the closest one to about, I think, 70 AU for the furthest one. And what is interesting is that there's a mass estimate for all of these planets from their luminosity, and they all seem to have more or less the same mass estimate. So all of these planets seem to have the same mass from between 5 to 7 times the mass of Jupiter, again, based on the luminosity. So it's model dependent. And the fact that this mass does not seem to vary much with distance actually fits much better one of these viscous lines than the inviscid line, the steeper inviscid line on which we focus on this talk. But that's only one system. We'll have to collect more statistics to see which of these slopes, if any, real systems follow. And this might hint something about the strength, the extent of the viscosity in these disks. Okay, so I'll summarize the talk. So planets get, to their, yeah, it seems to fit, right? So giant planets get to their large masses through a runaway growth process, which is essentially the result of ever-shortening Kelvin-Helmholtz cooling timescales. And one way to stop this process, so somebody suggested I should put Goldreich and Tremaine here, but I haven't. So one way to stop this process is when planets open gaps in their disks. So this is a very old idea. It's been around for several decades. I think that one of the new ingredients in this work is the realization that planets and gaps evolve together. So we must have a self-consistent and time-dependent theory that couples the growth of the planet to the deepening of the gap. And when you do this properly, you get a limit. You get a closed-form expression for the planet's mass, final mass, in the inviscid limit. And this final mass does not depend on the Shakur and Tsunaev alpha parameter. Depends very weakly on the disk's lifetime. It basically depends only on the aspect ratio, H/A, and on the ambient density, or the total mass of the planet. And it gives roughly the right scale. Now, before I finish, maybe one more minute, this workshop is called Challenges in Planet Formation Theory. And I think that this plot demonstrates one of the challenges of these gap opening theories. So this shows how deep of a gap you should have in order to stop the growth of a planet at any given mass. So this is given by this dotted black line. So if you want to stop at the mass of Jupiter, you need to have a gap which is as deep as about 10 to the 5 compared to the ambient disk. Now these are very deep gaps, and this result is independent of any specifics of any gap opening theory. It's simply comparing the Bondi accretion rate to the disk's lifetime. So I hope that I convinced you that we do have a one-dimensional, even analytical theory that does reproduce gaps this deep at more or less the right masses. So this is overlaid here by these colorful lines which cross this line at some point around a Jupiter mass. But the real question is, as I learned flying over here over some thunderstorms yesterday, multidimensional effects such as turbulence and vortices are also important. And the question is, can multidimensional instabilities, multidimensional simulations, which take into account these and other multidimensional instabilities, can these simulations also reproduce such deep gaps that are required to explain the masses of gas giants? And with this challenge, I'll end up and take questions. Thank you.
Yes, so this is quite interesting. So you mentioned that, of course, HR799 is one system. I just want to point out that things will improve quite a lot quite soon. Now that Gaia is going to find a lot of giant planets right where you need them to test that.
Exactly. So yeah, so I hope that we'll have at least several more systems like this with multiple planets. Yeah.
Yes. So we're going to get a statistically sized sample to actually test this. I think this will be quite interesting in the next few years.
Yeah, exactly. Yeah.
Related to your last point there, but so heuristically, you might expect the wake of a big planet to cause a lot of turbulence because it's something people see in experiments and simulations. Wouldn't this then increase the effect of alpha a lot? Because it would act as a turbulent viscosity, so the planet effectively causing its own alpha, which could then cut this off a lot earlier, I guess. Do you have I mean, you already said this, but do you have any other comments?
So most of these instabilities go to this direction, that they basically limit how deep of a gap you can open, which is a problem if you want to explain the final mass of gas giants with gap opening. Yeah, so that's exactly the challenge. So I do see some simulations that do get gaps as deep as about 10 to the 5 or almost there. But other simulations immediately run into instabilities and and then they don't get as deep.
The physical viscosity of the simulation might be an important parameter for that, because if they have a low physical viscosity, they'll be more likely to develop turbulence and therefore limit their depth. Perhaps.
What do you mean by physical viscosity?
Like the resolution or the actual viscosity they use, not an alpha.
Exactly. So that's the reason I said that this problem is more easily solved analytically than numerically. So computers are better than humans in most things, but actually in this problem, if you want to go to really low viscosities, which are required if you want to get deep gaps, then today's simulations have a runtime problem because you have to have a very fine resolution in order not to have a numerical viscosity. And then when you go to a very low resolution, you can't run these simulations for millions of years, and that's what you need to have, because you don't actually reach an equilibrium. Or even if you reach an equilibrium, you reach it only after several million years. So that's exactly the numerical challenge here. And I think that numerical simulations are almost there, but they are not quite there yet. We can't get to the right resolutions over the right timescales. So today, most simulations just run for a limited number of orbits. So that's one of the challenges. Yeah.
Important effect on these results.
Yeah, so that's an excellent question. So obviously, if we'll have migration here, it will almost by definition be type 2 migration because we open a gap. And frankly, I don't think that we as a community understand type 2 migration well enough. So obviously, the way to do this properly is to couple both planet growth, gap opening, and type 2 migration together. And now we coupled only the first two without the planet migration. Yeah. So obviously we need to couple type 2 migration. I'm just not sure that we understand type 2 migration well enough. But yeah, it's also coupled to the growth of the planet and the opening of the gap, right?
The final mass of the planet will increase or will decrease if you include, for example, migration?
Oh, let's think about this together. Okay, so let's assume you migrate inwards. And then, okay, so I would expect that as you migrate inwards, then, on the one hand, gaps become easier to open when you go inwards. But on the other hand, the Bondi accretion rate becomes larger when you migrate inwards. So, okay, I would guess because of the, let's go the other way. So it's just a guess, we should do this properly, but I'm guessing that because we seem to have larger masses further away, I would guess that if you migrate inwards, you would expect to find, to end up with a lower mass, because you migrate to regions where you would have reached a lower mass if you've developed there. On the other hand, if you look at a constant semi-major axis, some of your accretion happened further away when it was easier to go to larger masses. So yeah, but we have to think about this. Yeah.
Maybe some simplification here. You are assuming that everything scales with density inside the gap, but actually the planet is get fed by the circumstellar disk through the gap, quite a large amount. If we talk about a Jupiter at 5 AU, then we are talking about 10 to the minus 6 Jupiter mass per year of feeding from the vertical direction, and there is circumplanetary disk as well, and so on. So it's maybe not the density of the gap what you're scaling with, but you should look at the vertical influx, and for that you need to do 3D simulations.
Yes.
And I think it will scale with that density maybe, or how much accretion you get vertically.
Yeah, so I think that I agree, but I think that, let's go back. Yeah, I think that if you go asymptotically to the limit where you're much below the thermal mass, where the Bondi radius is much smaller than the Hill radius, then I would guess that this effect gets weaker and weaker. So you're right that when we are still in the comparable regime, where the two already are similar, then you have these streams coming into the gap. But I think that when you go asymptotically to very small masses, which is not exactly the case, and that's why we do need the simulations, I expect that asymptotically, these streams will get less and less dominant because all this multidimensional action happens on the scale of our Hill. And by the time that you get to the Bondi radius, you get a flat density. So I would guess that asymptotically, this is the answer you get, but yeah, I guess that you're right. When the masses are still comparable, then right, you have to check this against simulations. And yeah, a Jupiter at a 5 AU, so yeah, I should have said that. Yeah, so a Jupiter at 5 AU, it's 1, 2, 3, 4, 5, is actually above the thermal mass. So yeah, Jupiter a Jupiter at 5 AU won't follow this theory.
Yeah, but I think Chris Orma find that also at Earth mass planets, it's the same circulation that you have accretion vertically and outflow in the midplane. Am I right, Chris? So
I think these are close in Earth mass planets, right? So these are again planets that, so yeah, the closer you get, the lower the thermal mass gets, and then we have to keep, our theory is valid only below this black line, below the thermal mass. So the inner you get, the less this theory is valid. So when you get further out here at 100 AU or at 50 AU, then you're okay. But yeah, when you go to 1 AU, then or to 0.1 AU, then even Earth mass planets become problematic because they exceed the thermal mass.
Slightly related question. So your theory is valid below the thermal mass. And so as Goodman and Rafik showed, then the wave starts out linear, propagates, shocks, deposits angular momentum. So you get a gap away from the planet.
Right.
So the planet is still fully embedded.
Right,
so
right.
how is that going to affect the equation?
Right. So yeah, so if you have only these Goodman-Rafikov waves, then actually nothing happens at the location of the planet itself. So basically you have to rely on some viscosity to smooth the inner edge of the gap, to relate the place where waves impart the angular momentum to the place where the planet itself is located. Right, and so we do assume that we do reach viscous equilibrium in the planet's region, even if we don't reach viscous equilibrium on larger scales further away at the edge of the gap. Right, so we have to have some viscous process to, yeah.
The distance from where the wave shocks to the planet is the same scale as the gap scale, right?
Oh, no, it's a bit more complicated because then what we show is that actually these gaps are composed of these sort of two steps, that there's these waves that dissipate the angular momentum, and then this location where the waves dissipate becomes the dominant wave excitation region, and then you have a wider gap. So it's not exactly the same location when you get to really deep gaps. We can talk about this later, maybe.
I think I'll cut it off there. Thanks again.
Thank you.